Okay, so first of all, can you hear me? Perfect. So, do you have questions about previous previous classes, previous seminars, anything? Just before I start, I think I messed a little bit with the topics because I think Marcus changed the plan once, and I didn't see that. But I think we are on track. I think I just skipped maybe a few exercises, like 11 point something. But yeah, I mean, as I said, as I've written in the announcement in the very beginning, you are welcome to influence my selection of the problems via email, or just say, please solve this exercise, and I will try to do that. Yeah, so if you have questions, otherwise, I'll start with today's topic. And let me just open the book at the correct page. So we are in section, we are in chapter 12. 12.4. Yeah, so we are going to give a look to a bit of calculations of, So is it possible to try and do some exercises from the sheets today? Yes, sure. At least the latest one. Yes, you can do them. So maybe I will dedicate maybe 15 minutes or 20 minutes to those. Maybe you can if you have some preference, you can tell me. Otherwise, I will solve the sum of them. Here, I think. Let's see. Yeah, I have some of them done. So yes. Okay, so let's start giving a look to something simple, and then so this is seminar number 5. Number 5, and today is the 15th of September. Okay, so exercise number 4.1. Yeah, so here we just want to compute all the partial derivatives of second order of the given function. So we have this function f of xy of x is equal to x squared times 1 plus y squared, and we want to compute what the book calls f11, f22, and f12, and actually f21. So f11 of xy, which is nothing but second order partial derivative with respect to x, is going to be equal to the partial derivative with respect to x of the partial derivative with respect to x, with respect to x of f. So this is equal to the partial derivative with respect to x of 2 times x. This, as usual, we keep the other variable constant, but then we have to differentiate one more time with respect to x, and we get 2 times 1 plus y squared. And similarly, we do for the second argument, right? So this symbol is what in mathematics is called an operator, right? You will see them, you will see such kind of operator is essentially a function that takes a function and splits another function. And indeed, if you think about that, the derivative is an operator because it takes a function into an argument as an argument, and then it gives you another function. So this is equal now to the partial derivative with respect to y of let's see, x squared is the same times 2 times y. And this is equal to 2 times x squared, right? So let's see the mixed partial derivative. So now this is partial with respect to y, respect to x. Okay, so we have that this is equal to 4 times xy, and f21, we differentiate first with respect to, wait, yeah. So this is this, and then we differentiate with respect to x, and we get again 4xy. Now a question for you. As you have seen that, so notice that f21 is equal to f12. Is this a coincidence? Or if not, why? Why do we have this equality? Any idea? No ideas? Okay, so I don't see answers in the chat. So yeah, no, this is not a coincidence, of course. Okay, let's see. The function is C2 smooth. We proved that on the lecture today. They commute. Yes, very good. That's called the Schwarz theorem. So that's the correct answer. So since the function is C2 smooth, you will have that the mixed partial derivatives of second order are the same. So no, it's not a coincidence. And I write CFR, Schwarz theorem. That is the one that you're mentioning now. Okay, good. So I'll do, yeah, okay, I'll skip the number 3, which is very easy. I can do maybe number 6 just to get used to this kind of calculations. The task is the same. We still want to compute the partial derivatives of second order of the given function. Now the given function is this. We have logarithm of 1 plus sine of xy. Of course, when you find a problem like this that says compute the partial derivatives, you can always, cook up your own problem and start thinking, what's the domain of this function? What's the biggest set of the domain where the function is continuous? Is partially differentiable there? Is it the partial derivatives are continuous there, and so on and so on. So there are a lot of things that you can ask yourself about about functions like this. So for example, this would be interesting to compute the domain and see if what happens at 0, for instance. But let's stick with our task. We want to compute partial derivatives. Now I'll start with the first order, which is easy. So we do the chain rule. This sine of xy times cosine of xy times y, right? And then we do this also. We have x cosine of xy divided by 1 plus sine xy. So from here, we get that second order partial derivative with respect to x. You do again a bit of chain rule. you get this squared, and at the numerator we get minus y squared, the sine of xy, times 1 plus sine of xy, minus y squared cosine squared xy. This is equal. Now I go to the other page. This is equal to, because you do simplifications, right? You get minus y squared times 1 plus sine of xy, right? Divided by 1 plus sine of xy squared, and then you can simplify this. So you get minus y squared divided by 1 plus sine of xy, right? And similarly, you can prove that so the second order with respect to y, you do some calculation. I'm not doing them, but you get this essentially by symmetry, because I mean, it's the calculations are identical. There is no difference with respect to the previous one. Instead, we're differentiating with respect to y, and the mixed ones where the function is c2. Well, actually, this holds true probably in the domain. So we get that this is equal to 1 plus sine of x, y, and then we have cosine of xy minus xy sine of xy minus xy cosine squared of xy divided by 1 plus sine xy squared. So this is equal to, you do simplifications. Maybe I can skip them. Yes, I can skip them. You simplify the expression and then you get minus xy plus cosine of xy divided by 1 plus sine of xy. And that's all. Yes, so these are just mechanical computations. I don't expect this to be hard for you. Okay, so let's see exercise number 9. So we are introduced to this concept of harmonicity, harmonic functions. Harmonic functions are very important. You will see why harmonic functions are important in more advanced courses like PDE or function analysis. So we say that, let me recall that we say that a function function f, actually I don't see any limitation on its domain, so we can say that it's Rn. A function like this is harmonic if the Laplacian of f is equal to 0. So what is the Laplacian now? Where this guy is the Laplacian operator, or Laplace operator is the Laplace operator. And this is defined as, okay, maybe I can use x1 because I have n variables. So it's the sum of this partial derivative of the second order. So this means that the Laplace operator computed at f is nothing but exactly what you would expect. Plus this plus dot dot. Yes. So a function is said to be harmonic if the Laplace is its Laplacian or Laplace operator is equal to 0. Okay, so given that, we want to prove, that f of x, y, now we are in the case in which n is equal to 2, so we are in the plane. So we want to prove that f defined by this function, this polynomial formula here, we have 3 times x squared times y minus y to the power of 3 is Laplacian, is, sorry, harmonic in the whole plane. So it's again an exercise in computing partial derivatives. So we have that the second order partial derivative of this function is equal to what? So the y to the power of 3 is killed, so we differentiate 2 times. So I think we get 6y, right? And when we compute this, the first term goes away because we have just a degree 1 polynomial in y, and the second is there, so we have this. So as of course we expected, the sum of these two guys is equal to 0, so the function is harmonic. And then there is another question that says, can you think of another polynomial of degree 3 in x and y that is also harmonic? Yes, so other polynomials of degree 3 that they are harmonic. And say harmonic polynomials of degree 3. Well, you can define, for instance, I picked a family of polynomials of degree 3, 2 variables. So I picked this. Of course, you can, yeah. So cxy to the power of 2 plus dy to the power of 3. So I have a family of polynomials now. And I can see if I get some conditions on A, B, C, and D, such that this guy is harmonic. So if you take the derivative with respect to x of the second order, you get this is equal to 6ax plus 2by, and then I have this, this is equal to this, 6dy plus 2cx. So this is what we have. So we want the sum of these two guys to be equal to 0. Yeah, I've written f, but this is p and p again. Oh, we want this to be equal to 0. So what is this? So we have 2x times 3a plus c plus 2 times 2 times y, right? Times 3d plus b equal to 0. So now this has to be true for all x and y, right? So the only way to kill them both is, so this is true, essentially if and only if 3a is equal to minus c and 3d is equal to minus b. So these are the conditions. So we have plenty of them. We have infinitely many of such polynomials. And yeah. Okay, so this was a exercise on harmonic functions. we can try to do the number 11 too. Number 11. So we have the function f of xy, which is defined as this. So we want to prove that f is harmonic in R2 minus the origin. Why are we excluding the origin? Question for you. Exactly. Zero doesn't belong to the origin doesn't belong to the domain of the function. It doesn't make sense to yeah, to investigate at that point. Very good. Let's see the partial derivative with respect to x. I can skip the intermediate computation. This is going to be equal to minus 2x squared plus this divided by x squared plus y squared to the power of 2. And this is equal to 2x squared minus 2y squared divided by x squared plus y squared to the power of 2. So of course you see that this is equal to minus the partial derivative with respect to x. So we are good. Okay. Right. Where is number 15? Okay, so we have the number 15 now. Well, also this one is quite easy because we have two functions, so let u and v be C2 functions, C2 smooth functions. Such that they satisfy so-called Cauchy-Riemann equations. Cauchy-Riemann equations are very important in complex analysis. So what are the Cauchy-Riemann equations? Let's see. So you want this mixed cross conditions, I don't know how to call them. So, and the partial derivative with respect to y of u is equal, well, it's not like it is written in the book, let me just stick with that. P with respect to x is equal to minus u with respect to y. So the claim is now, so let u and v be C2 smooth functions such that they satisfy the Cauchy-Riemann equations, and these are the Cauchy-Riemann equations. Then prove that both u and v are harmonic. So we want to prove that the Laplacian is equal to 0. So we need to prove that the Laplacian of u is equal to the Laplacian of v, and this which is equal to 0. And then you see that it's quite easy to see, because if you take the second order partial derivative with respect to x of u, this is equal to, by the Cauchy-Riemann equation, I'm using star, maybe I can call this star and this star star. So using star, we get this, right? And this is going to be equal to minus partial derivative with respect to y, x, and then here I'm using star star, right? So now we started with the hypothesis that both functions u and v are C-smooth. So by the theorem that you mentioned before, so the Shor's theorem, we get that the mixed partial derivatives of the second order, they are the same. So since v is C-smooth, C2 smooth, partial this is equal to this, right? And this implies that the sum plus b, no, u, and this is also u, this is equal to 0. And similarly for same for b. So we prove that. If we have functions that fulfill the Cauchy-Riemann equations, we know that they are harmonic, and this is very simple to prove. All right. Let's see the number 16. Number 16. This might be an exercise that you can find in an exam, for instance. More detailed study of a function. So we have the function f of xy, which is defined by cases. So it's defined as 2xy, this divided by this guy, if xy is not equal to 0, and 0 if xy is equal to 0, 0. So, so we want to calculate f1, f2, f12, f21 for xy not equal to 0, 0, and also calculate those derivatives at 0, 0. And then there is another question, and then I will come back to. Let's start with this. So I wanted to show you something before going into computation. So for example, in an exam you might find something like this, but with some other questions. So like for instance, is the function continuous at the origin? So let me open. Let me answer to this question too, because you'll see why I want to do that. Okay, so I'll draw a line here. Is f continuous at 0, 0? So we have seen several of these exercises, and so this question, to answer this question, we need to compute a limit, right? So to check that, we need to compute what? The limit for y that go to 0, 0 of the function f of xy, right? Okay, so my claim is that indeed the limit exists and it is equal to 0. And I want to prove that. How do I prove that? So you can notice something very important is that this quantity, this f of x in modulus is controlled by the modulus of x squared minus y squared. Okay, there is a question. Is this not the exercise we were meant to do today? Maybe you're right. Let me check the schedule. Well, I am always confused with this because so Marcus wrote, maybe he wrote it wrongly, I don't know. So he wrote Friday's lecture is cancelled on Friday or on Thursday, and then he wrote the next lecture, which is the number 6, is on Tuesday. So if I go on the schedule, I see that the lecture number 6 is chain rule. So maybe today, maybe he did it wrong and he did number. Yes, I know, but then he wrote wrongly. Then the today's lecture was number 5, not number 6. That's maybe. No, we shouldn't cover the same topic. The idea is that the classes are we did lecture 12 in between 4 and 5 for some reason. Yeah. Well, I don't know. I mean, I'm a bit confused too. I don't know how to interpret this schedule. So he wrote number 6. So I thought that if today does the number 6, then I will do what's before, which is what I'm doing now. But apparently, it's not like this. Aha. Okay. Okay. So let me do this. I will finish this exercise, right? And then we can do something else if that's okay with you. So we leave the leftovers from for the for the next time, and we can do maybe some exercises from the sheet of exercises that I've never done. So if this is okay with you, I will finish this problem, and then I will go back and see and do some sort of maybe a bit of recap of what we did, so you have time to catch up with the new material, and then we can proceed. So, but you did good that you tell me, because I was not sure too. So, okay, so let me finish this and then we'll see. So, by the way, I mean, I could actually stop here immediately after I prove the continuity, because continuity is something that you did already. So why is this inequality true now in this? So this is a very important inequality that I suggest you to remember. It's very easy. Important inequality. So if you take this, right, this is a square, and by definition, the square is greater or equal than 0. So if you expand the square, you get that this is right, greater or equal than, and then I take the modulus here, product of moduli, which means that you have a very nice inequality. This is less or equal than 1 when xy is not the 0, 0 point. So if you see, I'm using that here. right? There is a modulus. There are some moduli, but you know that, I mean, this is equal to this. So using this inequality, we get that this quantity is, I mean, the red potato here that I drawed here is less or equal than 1, so it means that the whole quotient is less or equal than the modulus of x squared minus y squared, and this is clearly going to 0 as y x go to 0. So the conclusion here is that f of xy is continuous at 0, 0. Okay, so I'll stop here. I'm not going any further with this problem. We will go ahead with this problem tomorrow, hopefully. And okay, let's do in this way. Now it's 10:52. Let's take now the break, 15 minutes of break. I'll go through the old seminars solutions, and I will find some exercise to do in the next class that are not about second order derivatives and things like that. So we start again at 11 and 7 minutes. And if you have questions, you can ask them now or write them in the chat. Okay, let's see. Yes, this is what I'm. Well, I mean, I'm answering to Oscar. So the next seminar, which is tomorrow, I will do what I haven't done this morning. So the second half, a little bit more than the second half of this chunk of exercises, and then I don't know, because it depends on what did you do today? Did you do anything about differentiability of functions? So the definition of okay, so that's nice. So yes, then I can go through exercises on differentiability too tomorrow. So at least, so you have at least one day to give a look to the material. It's not good to do them today because you need at least 24 hours to give a look to the things. So yeah, I mean, yeah, tell him please, because I am confused too. I mean, he should be a bit more precise in what he writes, because so yeah, I mean, yeah, as I said, I maybe I misinterpreted his announcement, but he wrote next class, which is the number 6. It will be on Tuesday. So in the plan, I read that lecture number 6 is about the chain rules. So I thought that you did higher derivatives and differentiability and linear approximation on the last one. So okay, so you guys you guys tell him, and I also tell him. Okay, so because now he's not here, he's actually my supervisor, so I'm quite in confidence with him. So no worries, we will fix this. So I will ask him to be more specific and more detailed in. I think he should simply add dates on the, not just lecture 3, 4, 5, because one wants to keep track of the thing. So you guys tell him, and I'll tell him too. So let's see what we can do. Okay, guys. So I spoke with Marcus right now. I called him. So um he's going to update the plan, hopefully with adding some dates. And he also said that today's I mean this lecture six thing was a mistake. So um, okay, but it's not too bad. We can go through some old exercises from this sheet of exercises, number one or number two. I don't remember. I have some that I haven't done, so we can do some of them. Let's see if you have some. Yeah, if you have some questions or just to type them or just to speak. Okay, so we have this sheet number one. There were few limits to compute, and in particular, I want to give a look to exercise number 9 and number 10, and then also to number 7, which is more complete, a more complete exercise. Okay, so here we have a function in 3 variables instead, and we want to compute a limit. So the task here is to compute the limit for x1, x2. Okay, no, I don't know if I have to use x1. Okay, let me use xyz. That's the same thing. We have 3 variables here, and we want to compute this limit e to the power. Okay, so let me also introduce the notation x kind of capital letter. So, and this is just a vector, right? Or a point. Now we want to take the norm squared of this, minus 1, divided by the norm squared plus, okay, so here it's x1 squared, so it's x squared times y plus y squared times z. And let me check that I'm solving the correct one. Let me see, sheet number 1. Yes, so that's, I'm just replacing x1, 2, 3 with xyz because it's faster to write. Okay, so what is this? So you remember what's the norm, right? Of a vector. So we have the limit for x, y, z that goes to 0, 0, 0 of e to the power of x squared plus y squared plus z squared minus 1 divided by x squared plus y squared plus z squared plus this here, right? Okay, and so I think that a good idea here might be to use, let me just check one thing. Okay, so here, a good idea. We can try to use here. We can try with spherical coordinates. Spherical coordinates are generalization of polar coordinates. Now, I wanted to give a look to your lecture notes because I want to be consistent with the angles. Sometimes somebody calls the angle theta and phi, so you don't get too confused. Let me see where he introduced such things. Where are the spherical coordinates? Quadratic. Okay, okay, so this is, yes. So spherical coordinates are in the first file of the lecture notes, file number 1. And recall that spherical coordinates are defined as x equal to r cos theta sin phi or phi, with this, and then y is defined and z is defined. So y is r sine theta sin phi, and z is r cos theta. And now you remember that r is greater or equal than 0, and then theta belongs to the opening interval, the half opening interval, this, and phi belongs to 0 pi half open. Okay, so we want to use them to solve to compute this limit. And why do we want to use them? Because of course, you know that we have nice properties, right? So so this limit, I can rewrite the limit here. This is going to be the limit for r that goes to 0, right? Of what? Of e to the power of, now we have x squared plus y squared plus z squared. If you substitute the spherical coordinates into that expression, you get only r squared, which is very nice, because here we have e to the r squared minus 1, and then at the denominator we get r squared, and then we have something a little bit more complicated. Let's see, we have r to the power of 3, and then we have cosine to the power of 2 theta, sine to the power of 2 phi, times sine theta sine phi again, right? And then you have again plus r to the power of 3. We have sin squared theta sin squared phi and cosine theta. No, it's wait a second. No, it should be correct. Ah, wait. Well, then there is a mistake in the lecture notes too. Nice. Yeah, I think you're right. It should be a phi. I'm always getting confused with these angles. That's why I checked, but let me see. Yeah, I think you're right, because let me double check with the book too. Spherical coordinates. Okay, so yeah, sin phi cos theta, which is what I've written, sin phi sin theta, which is what I've written, and cos phi, which is not what I've written, but what I've corrected just now. And phi is between 0 and pi, and theta is between 0 and 2 pi. Yes, so you were correct. Thanks. Yes, sure. Of course. Right. So let's continue with this calculation. So what do we get here? So this is equal to the limit for x that goes to c for z r that goes to 0. So we have e to the power of this, and then we have r squared, and then we have I can just collect r to the power of 3, and then there is something here that depends on phi and theta, but we don't care about that, because now we use essentially Taylor expansion, and we get that this limit for r that goes to 0, the denominator you can write that this is equal to r squared plus big O of r to the power of 3, or actually 4, right? And then we divide, we can just collect r to the power of 2, and we get 1 plus r times something which is bounded. So this guy here is bounded. So we simplify these two guys. No, actually, no. I have to do one step more. So this is the lim for r that goes to 0 of r squared times 1 plus O, big O of r squared, divided by r squared 1 plus r times something which is bounded. Now I can simplify, and what I get is 1, right? Because this thing in red goes to 0, and also this goes to 0. So we get that the limit is equal to 1. So this is actually a good example of limiting three variables, in which you need to use a spherical coordinates to solve. Okay, so questions about this limit here? I'll start write down the number 10. Okay, so we have a limit here. Want to compute the limit for, okay, so now we have to write x squared plus y squared going to plus infinity. So the norm of x squared plus y squared, sorry, the norm of xy goes to plus infinity of sine of xy divided by x squared plus y squared. So we want to compute this limit if it does exist. So any idea on what's this limit? Anybody want to make a guess on what this might be? Yes, Eric, that's correct. Why? Well, it's pretty obvious, but yes, that is correct. So bounded divided times something that goes to 0. So the limit is 0, and the motivation is pretty obvious. So I'll write it here just so you remember, since we have bounded times infinitesimal. Good. What about the number, the B one? So limit, again, for x squared, y squared, that goes to plus infinity. Oh my God, this handwriting. Plus infinity of xy times e to the power of minus this. What about this? Yeah, I mean, that's the principle of squeeze theorem, of course. What about this one? Any idea? This is slightly more tricky. Yes, that is correct. We have different limits. Actually, yeah, I didn't pick that those straight lines here, but that's correct. So this limit does not exist. The limit does not exist, and it is enough to let me call this guy here f of xy. The limit does not exist. Why? Because you have that f of x comma 0 is equal to 0, right? While if you pick f of x comma minus x, that's going to be minus x squared, and this goes to minus infinity. Okay, so this was a bad idea. Let me write it again here. That's because 0, and here we have x minus x is equal to minus x squared, and this goes to minus infinity as well. Okay, so there is something that I wanted to actually add, because this might create a confusion. So let me do like I used to do in the previous note. So just to define the map phi1 of t as t0, and then you get that this is equal to 0, so it goes to 0 for t that goes to plus infinity. And then I define this other map here, t comma minus t, and then I have this, which is equal to minus t squared, and now this goes to minus infinity as t that goes to plus infinity, right? So yeah. Okay, so this limit does not exist then. So okay, so let's see. I had something else here. Let's see. Okay, to avoid confusing my lecture notes, let me just put them away. Okay, this is the number 3. Okay, there was this exercise number. Let's try the exercise number 7. So we have now a function. So we have a function which is defined by cases. Again, xy divided by x squared plus the modulus of y. If xy is not equal to 0, and 0 if xy is equal to 0, 0. So we want to answer to 2 questions. The number 1 is determine whether f is continuous, and the number 2 is find its range, which is not really yeah, it's not really a topic covered in. Well, you know what is a range, but okay. So what is the range here? It's range f of. So that's the set of the points f of x, y, such that this belongs to R2. We want to, yeah, we want to determine to find its range. Okay, so this doesn't seem, okay, so solution. Let's see how I did, what I did. Um, okay, so number one, my claim is that indeed the function is continuous at 0. So claim f is continuous at 0, 0. Why? Because if you take again the modulus here, this is going to be less or equal than that. And put an absolute value here. And then at the denominator, I put a maximum between x squared, right? This is always true. Because the maximum between the two guys is clearly less or equal than the sum of them. So now, in some sense, one would like to yeah, you know, to see the two different cases, right? So this is equal to xy divided by x squared if x squared is greater or equal than the modulus of y, or this is equal to the modulus of the sine of y times x if the modulus of y is greater or equal than x squared. So we have these two cases here, right? Yeah, right. So let me call case number 1 and case number 2. So it's clear that in both cases we go to 0. So in one, we have that x, y divided by x squared, this is less or equal than x to the power of 3, maybe modulus, divided by x to the power of 2, because we are in the hypothesis that x squared is greater or equal than the modulus of y. So this is actually now equal to x, and this goes to 0 when x goes to 0. And in 2, we have that, of course, the sine of y times x goes to 0 as x goes to 0 or y goes to 0. So in both cases, we go to 0. This means that this implies that the limit for x, y of this plus the model, this goes to 0. Right. Questions on this so far? So the conclusion is that f is continuous at 0, 0. Yeah, the sign appears because we have, well, actually we don't even have that sign, right? Because we have the modulus of y, and then above we have the modulus of y. So I can actually remove that. it doesn't really make any does any it does any well, it doesn't do any contribution. So yes, because here we have I mean in the end we have xy divided by modulus. I mean this you can write like if you want to less or equal, and then you simplify, and then you just get the modulus of x. So why did we start by taking the modulus of the whole equation? Because I wanted to prove that that limit is equal to 0, and I wanted to control the modulus of that function with a something that goes to 0. So you could actually do the same without the modulus, but then you have to find an upper bound and a lower bound, and then you have to prove that both the lower bounds goes to 0. But it's easier if you take the modulus because you have the same upper and lower bound by symmetry. I think if you take the modulus, it's easier. So yes, that's what we want to prove. Yes, exactly. I mean, in the end, proving that, I mean, if I prove that limit of this with the modulus, this equal to 0, then implies that, of course, the limit of the function itself goes to 0. So that's what we are doing. Yeah, the delta and the epsilon is not. I mean, now we are computing limits using like the algebra of limits, while I mean it's implicit here. You have a function, and then you have an f of x. Here you take the modulus. You want to prove that this f of x is controlled by something small, arbitrarily small, arbitrarily small. So when you're done with that, you're essentially saying that. Okay, let me write it down, maybe in another page. So what we are doing here, so we don't know if limit for x, y goes to 0, 0 of f of x is equal to 0. But if we find a function g of xy with limit for x, y go to 0, 0 of g of xy equal to 0, and modulus of f of xy less or equal than g of xy, then this would imply that minus this is less or equal than this, which is less or equal than this, and then the conclusion follows from what's called the what is called that theorem now? The not. Sorry, I couldn't hear you. I have. Oh Jesus! In Italian, we call it the policeman theorem, but the squeeze theorem. Thanks. Squeeze theorem. So that's what KGB. Yeah, I guess. Yeah, I guess that's close to what we used to call it. At least in high school, it's called the policeman theorem. But anyway, so without going into police or things, So that's the idea. So I can leave it here, but this is very and a bit hand waving, but it gives you the idea of what's going on. So that's why I took the modulus. Okay, so we proved this. So of course this argument can be maybe refined to in order to make it a little bit more elegant. I was thinking that one could maybe, no, but it should actually fine. Um, no, it should be fine. Okay, so let's see. Okay, so we proved that now the function is continuous. So that's quite important. So the conclusion is continuous at 0, 0, and therefore f is continuous in R, in the whole plane. Which is something that it is now important because we want to compute what? We want to compute the range of this function, right? So, okay, so the point number 2, we want to compute the range. So compute f of R2, right? Okay, so what did I do here? So consider the function g of t, which is defined as f of t, t squared. And this is equal to t to the power of 3 divided by t squared plus t squared again. So we have actually, you simplify, and then you get t divided by 2. So this means that the limit for t that goes to plus infinity of g of t, it's equal to plus infinity, right? And also g of 0 is equal to 0. So it's clear that g of 0 plus infinity gives you plus infinity, right? And the same thing happens also the limit for t that goes to minus infinity of g of t, and it's equal to minus infinity. So this implies that g of minus infinity 0 is equal to minus infinity 0 because the function is continuous, right? And that's because g is continuous. So the continuous function send connected sets into connected sets, which is literally what we call the intermediate value theorem in analysis 1, and then this will be called simply connectedness of the image of a continuous function. Well, you put these things together, and then you get that literally f of R2 is equal to R2 as to R, which is the whole straight line. That's because, I mean, you found let's call it a sub-function, the one that we call the G, where we have this property. So yeah. So the conclusion is that the image is the whole straight line. Yes, nice. Do you have questions about this? This is again this is a problem that you might find in the exam. So beware, try to go through the steps and see if you understood them. And yeah, you might be asked to solve similar problems, compute limits. This is a very common exercise that you might find. Okay, so I think I can do the number 8 also, exercise number 8 from the sheet 1. All right, so let's see. It's again about computing limits. So compute two limits. So the first limit is xy that goes to 1, 1 now of this function, if they exist, of course. And then we have x minus 1. Okay, so if I call this function, well, yeah, if I call this function f of xy, again, this limit does not exist. Why it does not exist? Because you can do, for instance, f of t1 is equal to 1, right? Yes, it's constantly equal to 1. But if you take, for instance, the curve t square root of t, and now you have to send the t to 1 instead of 0. So t and square root of t gives t minus square root of t divided by t minus 1. And you can actually, oh, not x. And you can actually collect the square root of t. You can suppose that t is positive here, we don't care, we just need to find. So we can collect the square root of t, and we get the square root of t minus 1. And then here we get the square root of t minus 1, square root of t plus 1. And then you simplify this guy. And let's suppose that, okay, but t is going to 1, so we don't care about, we can take the square root with no problems. So this is equal to, then, this is equal to the square root of t divided by the square root of t plus 1. And this goes to 1/2 when t goes to 1. So the conclusion is that the limit does not exist for the same reason. Yeah, exactly. Well, I mean, I don't know if a 0t and tt works. It might, but well, it's that's the one that I chose. It's one option. So there are usually plenty of options. So okay. So this limit does not exist. There is a number b also. Compute the limit for x, y going to 0, 0 of sine of the square root of x squared plus y squared divided by the square root of x squared plus y squared. Now here the solution is obvious because we can use the polar coordinates. So we get that the limit for r that goes to 0 of sine of r divided by r, that's equal to 1. So the limit exists. Because we have the same here and here. So okay. Do you have questions about this? You have questions about this these things? Let me see one thing. Six is number 2. No, okay, so yeah. Okay, so the sheet number 2 is more advanced things about differentiability. So I guess that, yeah, I think I did pretty much what I wanted to do. There is so exercise. I have solved exercise number 2, I remember, and exercise number 3, 4, and 5 are easy, so I'm not gonna do them. It's about computing domains and sketch graphs of level curves and things like that. I could maybe do the number 6. Number 7 is done. Number 8 is done. Number 9 is done. Number 10 is done. Maybe I can sketch a little bit the solution of number 6 and then we just yeah, let me do this. Let's see. All right, so we have a function exercise number 6, sheet 1. So we have a function a. The point A is we have a function f of xy, which is defined by this. That's a very standard function to find. And what's the question here? Okay. Express this function in polar coordinates. So f in polar coordinates So what is f in polar coordinates is f of r theta is equal to 2 times r squared times cosine theta sine theta divided by r squared. You can simplify the r squared and then you get actually sine of 2 theta. This is what it is. Or yeah, 2 sine theta cos theta. At least let's say that for xy not equal to 0, 0. Right? So now the question, the tricky one, is which values can f assume as xy varies over the punctured disk given by this. So x squared, no, delta squared. And then another question is, does f become continuous if we define f of 0, 0 equal to 0? Okay, so maybe I should use red and orange. No, green. Okay, what about red? Okay, so okay, so this is a disk without a point, and I guess that yeah, I mean it's pretty clear that So no, f of xy is equal in polar coordinates to the sine of 2 theta, right? And the punctured disk that we wrote in Cartesian coordinates, you can rewrite this set is the set is the set of the points r theta where r is squared is strictly less than delta squared and strictly greater than 0, and theta belongs to 0 to pi, right? Because you have essentially this thing here, but we don't have the origin. The origin is excluded. So this means that now theta belongs to 0 to pi. So okay, so we can call this g of theta. So g of theta, g of 0 to pi is equal to -1, because the function is continuous and yeah, the set is connected. So you have -1 and 1. You have the maximum of that function, which is achieved at the point pi divided by 4. You have the minimum, which is achieved at the point 3 divided by 4 pi. So the conclusion is that yeah, so the range of this function is -1, 1 for all delta. And yes, so the other question is, can we extend this function by continuity? And the answer is no. No. Consider f of 0t, which is equal to 0, and f of tt, which is equal to 1. So the answer is no, the function cannot be, f can't be extended in a can be extended by continuity at 0, 0. Yes. Okay, so do you have questions about what we have done today so far? So as I said, so since we have, so a brief recap of what we've done today. So I have started doing exercises in higher order derivatives, but since the class about higher order derivatives and differentiability was today, I stopped at some point. I decided to go back to the previous to the exercises that I had no time to solve, so we solved them. Tomorrow we are going to do the second half of what I intended to do today, plus exercises on differentiability. Yeah, so yeah, that is all. I'll stay here for a couple of minutes if you have questions and you want to, yeah, ask them. Otherwise, you're free to go if you don't have any. Bye bye. No worries. Thank you.